Thank you for joining us for today's interview. So we're going to be talking with Dr. Bernd Gerhartz today, who's the VP of Technology Development here at Abcam. Hello, Bernd.
Hello, Lynn.
So what we're going to do is we're going to discuss really what motivates Bernd and why is he so passionate about science, about working in the life sciences, and what he's doing here with us at Abcam. Thank you so much for taking the time to have a chat with me today.
Pleasure's on my side.
Clearly you have a great passion for the life sciences and for science in general. What makes you so passionate about this subject?
It's a thing of doing something new, something what people haven't done before. It's this adventure explorer gene in me which get addressed, and I can do things which are super interesting. So it's very hard to put into words, but it's something which makes fun. After being now more than 30 years on the job, I still have the same fun than the first day.
So 30 years is quite a long time to be doing one thing. So clearly you have to really enjoy what you do. So what have been the highlights of those 30 years?
I think one of the highlights was when a relative of mine who suffers from diabetes type 2 said that he got a new truck and it really helps him, and I was working on this truck. So I could basically, I was not a key member of the team, but I was involved in that. I did the protein for during the truck discovery process for that truck. It's a fantastic feeling when you can see that something which you created, where you are part of a team, does something really good for people.
That must be amazing. And I don't think there are many people that can say that they've had that impact on, just one life, let alone the many that you probably have with a drug like that.
It's very funny. When I then explain to the people what I'm doing on a day-to-day basis, they can't make the connection because it's so abstract. But I think I used to be always at the early stage of drug discovery, where ideas get born, and then you often don't see them evolving and getting to the market. But once now and then you have this feeling, and that's fantastic.
I think is typical sort of like time for a new drug to market, so sort of 15 years. Yeah. So, if you're lucky, you might get to touch one or two.
So I'm older than 50.
I think age is nothing if it's what you're really excited about. So while you're here, your area of expertise is in technology development. But before you came to Abcam, you were at Novartis for a number of years. What were you doing while you were there?
So I joined Novartis in 2002, and I was like 16 years in various positions. I started out my scientific career where I was interested in structure-function relationship of proteins. And the area I was coming in was proteases, so proteins which cut other proteins into pieces. And I did my postdoc on that, and then I had the opportunity to go to a small biotech company who was working on a diabetes type 2 drug targeted against one of these proteases. And from there, I went to Novartis because they were opening a new department, also focused on proteases and protease research in drug discovery. So I have a history of more than 20 years drug discovery. And it changed from going to proteins and to kinases and to all kinds of different target classes, but always in this very early stage of drug discovery.
Proteins is something that seems to be sort of cut through the whole thread of your career to date. What is it about proteins that engages you so much?
It's a fascinating thing. So we have 20 different amino acids and a few modifications on them, and you build a whole universe. By the way, they are folding, they get structured. You have a two-dimensional structure, you have a three-dimensional structure, you have a four-dimensional structure, depending on, and it is a flexible system. When we talk about drug discovery, we have this key lock understanding of that there is a key which fits exactly in a lock. That means you have a kind of a static system, and that is fine as a model, but in reality, it's by far more flexible and by far more interesting. There are pockets we can go open depending on what environment they are in. They are moving in all the biological processes are regulated by proteins. So it's a fascinating class of molecules.
They are complex in their very nature. Given that complexity and the flexibility and the role they play, how important is it to really understand the protein at the fundamental level?
It depends on what you want to do. If you want to understand, a lot of diseases are caused by misfunction of proteins. So if you want to understand what goes wrong in a certain physiological environment due to the protein involvement, you have to understand the mechanism, how the protein works, how it is folded. When I did my postdoc in Sweden, I was working on a protein which had a single point mutation in the gene. And the pure patients who had this, they were dying on brain hemorrhage in an early age, around 30 to 50, somewhere there. And the fascinating thing is that this small mutation within the protein is in the hydrophobic core of a protein. So proteins are usually structured in the way that everything which loves water is on the outside, and everything what hates water is in the inside. If you disturb that balance, you create an instability of the protein, and then the protein can aggregate and then cause a damage. So if you want to do something and develop a therapy, you have to understand what's going wrong, what is the function, what is the mechanism of the disease in order to treat it.
And how are proteins used? I mean, they're used very many different ways during the whole drug discovery and development process.
The first thing is they are studied in their cellular context, in their physiological environment. What kind of processes are they involved? What are they regulating, deregulating a certain pathway? Are they switching on something? Are they switching off something? So understanding the protein in a physiological environment is the first step. But then if you start developing a drug, you have to have an in vitro assay. So you basically have to bring the physiology out of the cell into an in vitro system in order to study it. And that we are usually using recombinant proteins for that. And then what is currently very, since a while it's top notch, is rational-based drug discovery. So we have a three-dimensional structure of the protein, and we can see how different effector molecules bind into the protein and influence the activity of a protein.
So you mentioned they're recombinant proteins. So what's the benefit of a recombinant protein? How is that different from a normal protein? Why would one want to go down the road of a recombinant protein?
The recombinant protein is the modern way of producing proteins. We have studied proteins like albumin already the last century, but then we had to purify that out of placenta or something else. The recombinant protein is a way to produce proteins in their natural environment. So we get the genetic information into a mammalian cell or into an E. coli cell, and then ask the microorganism or the cell to produce the protein in large amounts, and then we purify that and can use that for studies.
It sounds very simple. Is it very simple?
No, it's not.
So what's the challenges? And I think this is one of those things where we always distill down science into easy to digest steps, but then when you actually start to unpack those and go, actually, how simple is it? It's not that straightforward.
No, it's not that straightforward. The folding mechanism is quite complex, and we know a lot about how proteins are folding, but I don't think we completely understand that on all levels. So we have a certain try and error in order to find what is the best construct, what are the best conditions to produce protein in the right form, that it is stable, that it is well folded, that it has the natural functionality, which we also see inside the cell.
When you were putting together your team, what did you look for? What were the skills that really make a great protein scientist?
It's nothing what you can see on the face and you can explore in an interview. It's a skill set between your hands. Two people doing the same doesn't lead to the same results. There are this very talented, very skilled persons who know how to treat cells, who have a clear understanding when they look at their experiment, what are the parameters they have to change in order to get a better result. And yes, you can change all the parameters, but the difference between a very skilled scientist and a less skilled scientist is the number of experiments they need in order to achieve the result.
So you came to Abcam, you had a vision for what you wanted to do, and you've been exploring the vision and pushing the boundaries of that vision. Where do you, what has been your proudest moment so far?
The moment I got the data that we can in Abcam produce the quality of the proteins we wanted to do, that was the highlight, I would say. That is, we had everything planned, and we were quite sure that we were doing that, and we were promising that to the company. We do it in time, we do it in scale, but it's still this bit of a question mark behind that. And the team has worked hard. They produced the protein, they purified the protein, and then when we applied it in the activity assay and we were seeing that, yes, it has exactly the specifications we wanted it to have, that was a fantastic moment, and I immediately sent a big email to everybody involved, thanked the team. That was a great moment, and thanks again for the team. That was awesome.